la bibranche avec vous aujourd'hui, je dirais que c'est d'abord des rencontres. Des rencontres entre étudiants appartenant à différents laboratoires, différentes entreprises, mais aussi avec des chercheurs venant du monde entier. Nous accueillons tous les étudiants appartenant au domaine de l'électronique, au sens large. Nous donnons la possibilité à ces étudiants membres de créer leur réseau professionnel dans des domaines qui leur tiennent à cœur. Être membre bibranche, et donc membre I3E par extension, cela vous donne beaucoup d'avantages. Notamment, vous aurez accès à une grande librairie d'articles de conférences en électronique, mais aussi à l'actualité des dernières technologies et aux événements organisés par les entreprises de pointe. Mais avant tout, cela vous permet de faire partie d'une des plus grandes communautés scientifiques mondiales. Et tout cela pour seulement $20. Sur le campus bordelais, on organise des événements à peu près tous les mois, sur place ou sous forme de virtual event, au cours desquels on a des invités tels que des chercheurs. Mais on permet aussi aux étudiants du campus bordelais de transformer leur projet d'études en projet I3E, en ayant un soutien financier, et nous les accompagnons aussi dans l'écriture d'articles scientifiques afin qu'ils aillent en conférence par la suite.
Être à la bibranche, c'est faire partie d'une équipe dynamique et soudée pour promouvoir la science.
Pour moi, la bibranche, c'est l'occasion et l'opportunité de changer son quotidien d'étudiant. C'est l'occasion d'organiser tout plein de choses, des séminaires, des journées thématiques ou encore des concours technologiques autour de divers sujets scientifiques.
Rejoins la bibranche.
La bibranche.
Donc rejoignez tous la bibranche.
Únete a la bibranche.
C'est la bibranche, bye.
Unisciti alla bibranche.
It definitely changes your life. It helps you establish relationships that are really tighter because you already have a lot of things in common in the way you think, work, want to change the world around you.
As you get involved in IEEE, you really get a sense that you want to give back and to grow the community that you have.
I think there's a natural intersection between IEEE and its role in promoting the emergence of new technologies and entrepreneurship.
IEEE was a great channel to get to connect with professionals in the field. You never know what's going to happen when you meet so prominent people that are foreseeing the future.
What has IEEE brought me? I've worked full-time in power system automation, which we call smart grid, for over 41 years now, full-time. And the job changes I've made were through industry friends that knew of opportunities that I wouldn't have known otherwise and opened up the door for me. And many of these industry friends I met through IEEE.
What other place can you try to take a risk of doing our presentation skills and bringing in somebody from industry to talk to other scientists and engineers? I've been a member of IEEE for 25 years, and I still talk and mentor about this to this day.
IEEE has given me opportunities to network in terms of getting to know the leaders in the field, and also has provided an outlet for those leaders to know what I'm doing. So it's been good for both of us.
Given the world that we're living in now, where everything is pretty much about the internet and about connectivity, it's actually a good time to be an engineer and to be a telecommunication and networking engineer.
We know it's about the dynamics between people and people groups where our future is. And engineers can facilitate that, but they don't have the answers. It's the answering of us together as a community, not as engineers alone. So engineering is not going to solve the world, but it's going to facilitate that problem solving and getting together.
At IEEE, we believe technologists are the key drivers of tomorrow's innovations because we can really do what IEEE's motto states. We can advance technology for the benefit of humanity.
I always wanted my education to mean something more than just, doing a day job that pays my checks. I wanted to see how my background in engineering and other things could have an impact that can make somebody's life better.
Being able to connect our members with younger students and engaging them to emphasize that it is important, that what they are pursuing in their STEM careers is truly going to be the next thing that affects all of humanity, because all technology that we make is affecting people. And it's not just IEEE members, it's everybody.
Greetings everyone, and welcome to the new virtual talk of the series given by the B branch, the official student branch of the IEEE in Bordeaux. My name is Denis Flores, member of the B branch, where B stands for Bordeaux Electrical Engineer. And this day we have the pleasure to welcome here Professor Andrei Vladimirescu, who works in the University of California, Berkeley, and the ISEP in Paris. But before proceeding to today's talk, I would like to talk to you about the next events that are going to take place here during the next weeks, given by the B branch, and another interesting events that you might also be interested. So first, we are going to having here some different talks during the month of November. We already have several talks in the month of October. You can see them also if you by demand in our YouTube channel, but also in the next 2 weeks, we are going to have another presentation. The next presentation is going to be given in 2 weeks and is going to be given by Jean-Michel Valoutet from the University of Liège in Belgium, and is going to be more focused in electromagnetic compatibility in integrated circuits. It's also good to promote some other conferences which are going to be taking place in Latin America from the Candid chapter in Brazil and Argentina. There are going to be another conference in November 18 given by Daniel Enrique Muscano from Argentina. If you might be also interested in space engineer, there is going to be a virtual event in the 13th and 14th during this month here in Bordeaux. There is also going to be given some seasonal school from the technology and agrobusiness here in Bordeaux on how the technology is impacting the agrobusiness. Don't forget that the International Conference on Electronic Circuits and Systems from this year is going to be virtually also held by the Glasgow in Scotland. The ESCAS 2021 is going to be held in Korea, and now it's currently in the submissions of papers. So if you might also be interested, don't forget about it in the next year. Finally, there is going to be the seasonal school in the next year here in Bordeaux in his 3rd edition in the month of May and June. Well, before proceeding to the talk given by Professor Andrei Vladimirescu, I would like to give a short biography of him. Andrei Vladimirescu was the key contributor of the SPICE simulator at the University of California, Berkeley, releasing the SPICE 2G6 commercial grade program in 1981. He pioneered electrical simulation on parallel computers with the Classy simulator as part of his PhD and authorized the SPICE book, published by G. Wiley and Sons. Currently, he's a professor involved in research projects at the University of California at Berkeley and the Institute of Electronics in Paris, ISEP, and the Technical University of Delft, as well as consultant to the industry. Andrei is an IEEE Life Fellow and a member of the IEEE Circuits and Systems Society Board of Governors. And now I will let you, Professor Jan de Waal from the University of Bordeaux and the director of the IMS laboratory to welcome our guest.
Thank you, Denise. Thank you so much. I would like to thank all the people involved in this deep branch organizing those talks and invited me to welcome Professor Andrei Vladimirescu. Professor Vladimirescu is a close friend of mine. I can say that. I'm proud to say that. And it's a real pleasure. As you might know, Andrei, born in Bucharest, in Romania, and he made the very first of his study there. And then he joined the US at Berkeley University, where he pursued his master and then his PhD thesis under the supervision of the famous Donald Pedersen, and which means that at an age when some people snuck out of the house to have some fun, Andrei went over the wall as well, but it was the wall of Berlin, so we have to respect him a lot just because of that. So Andrei, please, the floor is yours.
Okay. Thank you very much, Jan, for this very nice introduction. Thank you, Dennis, also. And first and foremost, I like to thank the IEEE student branch of Bordeaux for inviting me to give this talk. Today, I would like to share with you a number of stories less known about the background, the events, the people who surrounded the development of this program called SPICE. As I'm addressing a group of electronic students who use or will be using this tool for designing circuits, I'm also going to touch on a few of the fundamental elements built into SPICE. The issues that I'm going to touch on are first starting with the history of the birth of SPICE. Why was it necessary to build this tool involving the design of integrated circuits? Some of the funny or less funny tales that I have that I remember from the many years ago, 40 years ago or so, when I started working on it. And then I will switch to the basics of SPICE, talking about equations and transistors, questioning accuracy, whether accuracy is more important or performance. And then in the latter part of my talk, I will address recent developments as well as new SPICE applications and conclude with some final thoughts. Well, you have here a beautiful picture, an aerial view of the campus of the University of California, Berkeley, the birthplace of SPICE. Among the different buildings, some more beautiful from the 19th century and some uglier from recent times in this picture, you can identify the hallmark of Berkeley, which is the campanile in the center. Now, some of you may have seen this picture before because Piazza San Marco copied it and they have their own version. This is a joke, okay? All right, now, what is SPICE? Well, the name says it all. It's simulation program with integrated circuit emphasis. So that is almost self-explanatory that it is intended for the design of integrated circuits. This program was the result of research work, students' research work at Berkeley. In a graduate class led by Professors Don Peterson and Ronald Rohrer, the students were given a project. So the whole class consisted in a project. And the purpose of this project was to produce the best available computer program for the simulation of practical integrated circuits. So key here is the word practical integrated circuits. Well, there were like 12 students who were crazy enough to take this class, where it was almost like everybody passed or everybody failed, depending whether at the end of the year Professor Peterson would accept and value the result of this research or not. Now, what led to developing this program? Well, just imagine we're at the end of the latter part of the 1960s. As you've seen in the previous week's talk, this is the time when, for the first time, more than one transistor was implemented into a single silicon substrate. Well, you've seen the 5 transistors that led to Kilby's Nobel Prize. Of course, there was not only Kilby, there was Fairchild Semiconductor with Bob Moore, Noyce, Grove. Everybody, when there is a new technology, or there is a new idea, let's talk about ideas. It doesn't happen in only one place. It's happening in parallel in several places. And eventually it leads to a new industry, like it was, in this case, the semiconductor industry. Now, on the right, you have the picture of one of the most famous analog integrated circuit designers, Bob Widler. Now, Bob is known, Widler is for his famous current source, which some of you may have already studied as part of your analog IC course. What is the problem with analog ICs implemented on a single chip? Let me take an example. The operational amplifier 741, released in 1966. It has not many, it has 22, 26 transistors on it. But as you very well know, the performance of an analog integrated circuit is very much based on its operating point. If we bias the transistors in the right operating points, we're going to get the performance we want and we expect. If we don't, the circuit is not going to work or it's not going to perform. So it was key to get a quick access to the DC bias point. And now remember, we have all these transistors who have exponential relations between the current and the voltage. And when you build a circuit in silicon, if it does not work when the silicon is done, you throw it away. It's not like a breadboard. As you can see in this picture, you have the integrated circuit chip, its layout, and you have the equivalent of this circuit implemented with discrete components. Obviously, when you have it with discrete components, it doesn't work like you want. You change a transistor, you change a resistor, and eventually you make it work. That's not true for silicon. So it was imperative to have a design that you are convinced it's working before you fabricate it. And this was like at the root of developing this program. Now, obviously, we understand the need. Now, how are we going to implement this? Obviously, on the old technology existent in the computer technology existent in the 60s, it would have been hard. There were mostly computers, old IBM computers were used mostly for economic purposes. Scientific computing was more demanding. You needed a longer computer world. 32 bits was not enough for many problems that had to be solved. So in Berkeley, we had since mid-60s, what is known as a control data company computer, the 6400. Now, here you can see the performances, which you'll probably laugh at what the performance of this computer was. So 10 megahertz, but it had a 60-bit word. This is important for precision. However, its internal memory was equivalent to that of the first PC introduced in 1983, only 64 kilowords, and eventually you'd get to 500 kilowords and get a disk of 10 megawatts. Obviously, it's laughable by today's standard, but this was the computer that we needed to develop this program on. Obviously, seeing the extreme limitations of the memory, it was necessary that whatever we described, however we represented the circuit in the computer, had to be very, very compact. Now, on another level, the computer access was not like it is today, that you could do like several hundred runs on your improving your program a day. There was what is called a computer-centered protocol. That means, as you can see here, the computer was in a temperature-controlled room with one operator who was responsible of feeding the computer with the programs to be run. Here you have magnetic tapes, so the medium on which programs were saved was a magnetic tape. And the way a program was entered into a computer, it was punched cards. So as a student, you had to be very nice to the person who would punch your cards, because one card contained one statement. So in its earliest forms, SPICE had around 10,000 instructions probably. One box, a heavy box of these cards, was contained 2,000 cards. So we had like 5 boxes. Luckily, we didn't have to carry them every day to the compute center. We just bring in the corrections and changes, but still, it wouldn't get more than a few runs every day. So this was the environment in which SPICE was developed in the late 60s. Now, the merit for launching this program, the promoter, the person who had the idea that this is a must in order for the integrated circuit technology to advance, was my PhD advisor, Donald Peterson. He obtained the IEEE Medal of Honor in 1998, and you see an issue of the Spectrum magazine, which you probably well know, the IEEE Spectrum, where he was named the father of SPICE. Now, when I arrived in Berkeley, Don was looking for a volunteer to take care of SPICE. So I was foolish enough to say, okay, I'll do it. So he named me the keeper, or if you want, the Tsar of SPICE in Berkeley, a role that I had between 1977 and 1981, and I don't regret it a single day. Now, you have to imagine that it was a gradual development. We didn't end up after the student project with a program that was running any type of circuit and giving you good results. So the first incarnation of today's SPICE was called Cancer. And this was a student, Larry Nagel. Larry Nagel, who was part of this class, he volunteered at that time to take all the different pieces. So one student, for instance, wrote the solution of a linear system, right? Another student wrote an integration algorithm for solving time-dependent equations. A third student wrote a little routine, a little program to express the behavior of a bipolar transistor. So Larry Nagel was the one who took all the pieces together, put it in a single program called Cancer, and that stood for Computer Analysis of Nonlinear Circuits Excluding Radiation. Now you would ask yourself, fine, every word makes sense, but why excluding radiation? Well, you have to, some of you were not born at the time, but if you go back to 1969, it was a year of a lot of protests, upheaval, that were not only in the US because of the Vietnam War, but also in France. Maybe some of you followed programs, films about Charles de Gaulle. This was the time when students especially got out in the street in 68, 69, leading to him going away for a moment before coming back. So anyway, it was a turbulent time. And so the students who authored it wanted to send a clear message that this program was not for building bombs, but for building circuits. Then, of course, somehow Don Peterson didn't catch the name quite quickly, but when he saw that the students named this program Cancer, he got mad. He said, how do you imagine that people are going to accept and use a program that is called Cancer? You have to change the name. So eventually, the students came up with the name that it has today, SPICE, which obviously it's self-explanatory what it is. And then in the Berkeley research, there were 3 generations. So SPICE 1 was a very simple program with a lot of limitations and somehow crude algorithm. The version that really made it, that created the link between the student project and industry tool, was SPICE 2. SPICE 2, the work was done between like 1975 to, I would say, 1981. I'm proud to say that SPICE 2G6, one of the last versions of SPICE 2, was a most reliable version that was actually used in actual designs in industry. Now, obviously, SPICE 1, SPICE 2 were batch programs. In the meantime, in the late 70s, the Unix operating system from Bell Labs became widely used, especially in universities. It took a moment before industry accepted it. But Unix allowed one to have a much more interaction with the computer and the software. Therefore, the newer project started in 1985, released in 1985, was SPICE 3, a re-architected program SPICE written in C and using all the Unix facilities such as interacting with the program, stopping it, questioning it, seeing live waveforms being computed. Now, SPICE 2, that made the link between a student project and industry, had a number of different releases. The first ones were Larry Nagel's thesis. Then I have to always mention my good colleague Ellis Cohen, who made out of a simple Fortran program an equivalent to a C program. What is the difference? You don't know Fortran, but in Fortran, you have to define at compile time how much space you allocate to each array. Therefore, you have to define, well, I can accept up to 100 transistors. I can accept 300 resistors. Now, you know, there may be enough memory there for the computer to handle it. But if you limit and you have 101 transistors, but only 20 resistors, the program SPICE 1 would not have run. So what Ellis did, he wrote a memory manager, the equivalent what malloc is for those of you who know C, in order to dynamically use the entire memory for the problem that it was given. Then, so this was SPICE 2E, which increased enormously the applicability and the usability of the program. Next, there was the issue that by the end of the 70s, bipolar technology was taking a back seat to MOS circuits. And the MOS models in SPICE at that time were very limited. I'll talk more about it later. So new MOSFET models were introduced. And eventually, accuracy was also, and robustness was also an issue for giving it to the industry. And a number of improvements in algorithm was performed. So 1970, the introduction of SPICE 1 and SPICE 2, and what was key to its success was the free distribution by UC Berkeley. You know, with every new technology, there are a lot of skeptics, and I will tell you a couple of stories that we had, you know, to weather during this development. Now, there are two main aspects of SPICE. First of all, there was a lot of algorithmic innovation, how to solve, how to represent and solve the circuit equations. And second, how to represent the behavior of the semiconductor devices. what we call today compact modeling, which later became a field in itself. And as I mentioned, you know, SPICE was, when it got, the time was ripe there in the late 60s, was not the only effort. There was an effort at IBM. There was an effort even in France. I remember a program called IMAG-3, and so on. So everybody was working in parallel. But remember, if IBM requested money from users in order to access ASTAP, SPICE gave it out freely to whoever wanted to test it and work with it. Now, number one skeptic, a famous designer, Bob Pease, whom you see here in this picture, and his breadboards, who declared publicly that there is nothing that SPICE does that I cannot do by hand. Well, you know, it took a little bit because, of course, he was a very respected person. So some of the people, it took them several years to accept that a time came when they couldn't do a design without using SPICE. So the free distribution also raised a number of problems. You know, it's the pain of success. I mean, success sometimes comes at a price. Now, we were like probably 3 students who were working together and were knowledgeable about the program, but the program was being distributed to a fairly wide number, saying, when I say wide, I would say 50, 70, maybe 100 versions that we sent out to different sites. So we had become, all of a sudden, instead of doing our research, we became like the people who were taking care of this program. So here is a record of a phone conversation I had with one of the people in industry, was one of the engineers who had the program. Says, "Hello, we purchased the SPICE program from you and it does not work." Very cut and dry, okay? So, you know, I was not a spring chicken either, so I asked him, "So how much did you pay for it?" Now the guy said, "Well, I paid $20. Okay, so then I had to lecture him and say, "Well, do you realize that, you know, we wrote a magnetic tape for you. We printed the documents and paid for the mailing. And also we needed a person to mount the tape to send the package and so on." Okay, all of a sudden, the person was so aggressive on the phone, kind of backtracked. Okay, so I said, "Look, you did not purchase the program. You covered just the cost of shipping the software." And at that point, you know, I had the guy asking for help. So it is very interesting in a conversation how you can get the person on the other end to realize what is real and what is imaginary. All right, let's switch gear now. What is the problem that SPICE needs to solve? We have a network, right? We have a circuit. And the first question you would ask yourselves is, okay, if I look at the schematic, it's obvious. But how do I represent this schematic in my computer? And the first thing we thought, well, we have to go by a matrix representation, and the nodal admittance matrix would be the ideal way to do it, because, you know, a node would represent the intersection of a row and a column in the matrix. So the topology was saved as an incidence matrix, where, you know, the nodes where a branch was connected were getting the 2 1s or 0s depending on the connections. Next, we had the 2 types of circuit equations that we need to implement and solve, which were the branch constitutive equations, BCs of the elements, the resistors, the diode. So the resistor is obvious, it's a linear relation between voltage and current. But what do we do about the diode? Well, the diode has, as you very well know, an exponential equations. So how do we solve that? Well, we thought, well, we do an approximation, and the next slide will show the approximation, which is pretty much taking the tangent in an operating point and replacing the exponential by a straight line with an intercept on the current axis. And then we set up the nodal admittance matrix system based on Kirchhoff's current law that you can see here. It's very easy to program this. All the branches that converge to a node are added in the diagonal elements of the matrix, and all the elements that connect two nodes together, they are going to be subtracted. They go into the matrix with some negative sign. The right-hand side is reserved to the current. Okay. Now we have set up this system of equation. Now we have removed the nonlinearity, so we have a linear system of equation that many of you know how to solve. But there is one important observation. Remember, we have a very small memory. But if we look at a circuit, let's say we have a circuit with 50 nodes. Is node I or node 1 going to be connected to all the other 49 nodes? Obviously, the answer is no. In most cases, majority of the cases, one node is connected to only another node. Some are connected to 2, maybe 3. But this is typically the amount of connection that you have. What does this mean? The off-diagonal terms in the matrix are these minus elements here. So if there is no connection between two nodes, that means that this element in the matrix, the off-diagonal element, is 0. So why would I carry all these zeros both as memory and operations? So the solution was to store just the non-zero elements of the matrix, which represent in many cases less than 1%, and operate only of them. So these are some of the key innovations. Now, I talked to you about replacing the diode by a straight line instead of the exponential. So, you know, we have like a companion model where you have the conductance representing the slope of the tangent in the operating system and the intercept, the current on the I-axis. Now you'll ask me, but how do you know that this is the operating point, right? Because we have a parallel resistor here. So really the voltage and the current will be given by the intersection of the load line. You can imagine a load line here intersecting these characteristics. So here you have it, okay? Now, we start with the trial operating point, the first guess. This is our first guess, and therefore we're solving the linear system, which gives us this solution. So this solution would be VD prime. Now, in the next iteration, so we're solving the equations by iterations. In the next iteration, we take this as the new operating point and replace the diode by a tangent in this point. So a new conductance represents the diode. And as we can see, the connection, the solution gets closer to the real solution. So after a number of iterations, we have a certain error tolerance, and we accept and we say that we have obtained a solution and the process has converged. Now, from the two things that I told you so far, we realize that there are two parts of the SPI solution. There are the nonlinear differential equations, or the equations representing the circuit, and there are the transistors that also need to represent and that provide by the derivatives of the current to the voltage the conductances that we need for the nodal admittance matrix, right? Now, they have different characteristics, and when we talk about speed of simulation, we have to take into account the ratio between the two. Here you have the flow chart of the solution, where you see you first start by linearizing the semiconductor devices. You have a linear system of equation that you solve. and you check if there was a previous solution, if the two solutions match. If you don't, then you delete a solution and you linearize again, as I showed you in the previous slide, the equations, again, linear solution, and you keep going in this loop. Now, once you have obtained a solution and assume you have a time domain solution, you go to the next time point. One thing that I need to mention is that in time domain, you take individual points, you discretize the time axis, so you do what is called a quasi-static solution. So if you learned you had some basic numerical course, you know the trapezoidal method of solving differential equation, and then you increase the time and repeat at each time point this inner loop. So this is the solution of SPICE. Now, obviously, to achieve at this point, to get to this point, there were a lot of innovations, starting with the input language. Now, today, most of you learn how to enter a schematic, and you never see that SPICE actually does not see the schematic, but this schematic is translated into lines of specification, which make a connection between the program, where you have to specify it's a resistor, it's a MOS, where it's connected, what its values, and so on. The second is the circuit representation. So in order to get the basic understanding, to give you the basic understanding, I just mentioned nodal. But nodal analysis is not enough. And you'll see in the next slide that we need to modify it in order to make it work. Then the nonlinear equation solution, again, it's a tricky thing because you need all those iterations to converge, which is not obvious. The integration algorithm, in order to be accurate, you have to have an implicit integration method. Also, in order to be efficient, you need to have a variable time step, because if you think of a circuit, at some point, nodes change voltage rapidly, and in other periods of time, they just stay put, they don't change for a while. So you need more time steps when there is a rising or falling edge, and you need fewer ones when there is no change in the circuit. We talked about sparse matrix solution, methods to store and solve only the non-zero parts of the matrix equation. And connecting all these different methods, we generally refer them to as direct method solution. Okay, the algorithmic part was the leading activity in the early days of SPICE. Now, obviously, nodal was not enough, and because why? Some of you who are still remember the details of nodal equation, I ask a question of you. If the voltage source is connected to ground, it's clear, because then you know the voltage at node 1. But what do you do with a voltage source which is connected between two nodes? Obviously, you know the voltage difference between the two nodes, but it doesn't tell you anything about what's the voltage on node 4 and what's the voltage on node 3. So the innovation here consisted of saying, okay, if we have voltage sources or voltage-defined elements like inductor, then we're not going to solve for node voltages, but we're going to solve for the currents flowing through these elements. Therefore, we need to expand the classic, you see equations 1 to 4 here, the classic part of the nodal admittance matrix equations, to add the two unknowns, the two additional unknowns, which are the currents to the two voltage sources, I1 and I2. So we augment the system by the number of voltage sources for which we represent the current. So now we have, instead of, for the circuit with 4 nodes, we have 6 equations. And this is called the modified nodal analysis, which, you know, is the basic SPICE solution approach. Semiconductor device models. Okay, so we said there is this second part where we have to represent the current voltage equations of the transistors. First decision was that this will be integral part of the program. Okay, Design engineers, they are not there in order to futz around with equations and device physics. They're there to build a circuit, so therefore everything needs to be encapsulated and made it available for him. In the beginning, there were just diodes and bipolar transistors because obviously this was the leading technology in the late 60s, early 70s. What I like always to tell to students who use the name model generically is to differentiate between an instance and the model. The model itself is a set of equations that is common to all the transistors. And then there are parameters who differentiate inside the same class of BJT for bipolar transistors, which is one or the other. So that would be the instance of each transistor, which has specifies the connectivity, the geometry, and other individual elements. So the model is common for a class of transistors, and they are described by the same equations. And then for each instance, we have typical its own geometry and connectivity parameters. Now, some of you may have heard of the Eber small model. It's a very basic one, very few parameters. Those were the first models, but as bipolar technology is dominant, there was a very accurate model known as the Gammel poule. For the MOS transistors in the early 70s, you know, they were like a curiosity, so there was only a very simple model. But by the late 70s, so like 10 years after the birth of SPICE, a number of the issues showed up as the dimensions of the MOS transistor got around 1 micron and below. So two new models, the level 2 and level 3, were introduced to take care of these aspects. Now, here is a refresher of the MOS transistors. As you see here, the structure is very simple. You have a silicon substrate in which you have two diffusions, the source and the drain. And on top of the non-doped, let's call it the substrate here, you have a gate. Now, the potential, the voltage on this gate is controlling what happens at the surface of the semiconductor. If I apply a high enough voltage, larger than what is called the threshold voltage, I will have a channel and current is going to flow from source to drain. Now, depending on the voltages, I have three regions of operation. The cutoff, when I have no conduction, the linear or resistive thing that you can see here, this is the region of linear operation, divided by the region of saturation, and it is divided by the saturation voltage, drain saturation voltage, defined as the difference VGS minus VT. Now, this is the classic all transistor, 1 micron or so length. So that's why this is known as the long channel transistor. Now, what happened when we got into the submicron region, right? We had leading technologies like 0.35 micron, 0.25, 0.18. Some of you may all still, in the PhD program may use a foundry that has 0.18 or 0.12. Well, when the dimensions got smaller and smaller, people realized that the MOSFET is not an ideal switch. You lower the voltage below the threshold, and then it does not lead current. No, it continues to lead current that we call sub-threshold current below the threshold voltage. And with shrinking dimensions, this current, not only that it flows, but it becomes larger and larger. And it becomes a nuisance when you think that you have a transistor cutoff, but it actually still consumes an important amount of current. A second thing that was noticed, you notice here in a classic transistor that the current is proportional to the square of the voltage, right? You can see it also here in the separation of the characteristic. You go to a short transistor, what do you notice? That they are equidistant. They are separated by the same amount of current for the same constant steps in VGS. So This is explained by what is called velocity saturation. Velocity saturation you can understand very easily. You have electrons or holes in an electric field, and you keep increasing the field, they go faster, therefore you have more current, right? But imagine you're driving a Ferrari. You are at 300 kilometers per hour, and you're still pushing the pedal, but the car is not going to go any faster. Same thing happens to the electrons. You keep increasing the field, but they will not go any faster. So that's why, because the velocity cannot increase, the number of electrons that go to the drain cannot increase, and therefore you will see the saturation happening much sooner. And the third important effect is the reduction of or the higher increase of the current in saturation, called drain-induced barrier lowering. And this is a pain for analog designers because the output resistance of the transistor is reduced. Now, for digital designer, it is important how quickly a transistor switches, and for analog designer, it's very important to know what is the bandwidth that the amplifier can have. And in order to be able to model this, we need to figure out what are the charge components of a MOS transistor, and you can see them here very schematically drawn. So the equivalent schematic would be this one, where we have two different components: the thin oxide components related to the gate, gate to source, gate to drain, gate to channel, or gate to bulk, and then the drain and source bulk junction, these junctions here, that is the type of the capacitance of a diode. Okay. Now, in SPICE, for many generations, we had this very simple model where capacitances are function of the voltage, as you can see here. When the transistor is cut off, we have all the gate capacitance connected to the substrate. When it starts turning on, we have first just the gate to source capacitance because the channel is cut off from the drain, and then eventually we go in the linear region and the two capacitances, gate source and gate drain, get the same. Now, in 1978, I remember one day I was in the lab and Don Peterson comes very upset, says, "Look what these guys from Stanford say. They say that our capacitance model is not accurate because it does not conserve charge." What were they meaning? Okay, so we kind of made this model because this was kind of working. This made sense, and not only that, but we built a number of analog circuits, op-amps, and so on, using this model, and we had verified it by measurements. But think of a different class of circuit. Let's say you have charge pumps where you constantly have pulses coming and charging up and charging down. Now, the observation of Don Ward and Bob Dutton from Stanford says, look, if we keep going and going with this pulse trains, eventually we see that we lose charge at the node. So what was the solution? Well, we have to consider that the transistor has three charge parts: the gate charge, the channel charge, and the bulk or substrate charge. Okay, so we have three charges, and the sum of these charges must the three charges must sum up to 0 in order to satisfy the conservation of charge. But there is an issue. We have three charges but 4 terminals. So the question is, how do we divide the charge of the gate between gate and source and gate and drain? Okay, so this really threw a wrench into our thinking, because what they were saying in their derivation is that you give 40% in saturation. Remember that a classic transistor has no connection between the channel and drain in saturation. There is the cutoff, so there is no connection here, right? So that's why in this model, you have no capacitance between gate and drain in saturation. But they said, no, there is capacitance. Okay, so I'm not going through the intricacies of this model where you have partial derivatives and non-actual capacitances. I'm just going to go to the result is that I implemented this model. I think I tested all the circuits that we have in our test suite. I installed by 3 a.m. The new version on the campus computer. And at 7 a.m. the next morning, Professor Bob Meyer, maybe some of you heard his name, he is the co-author of probably one of the best texts on analog circuits, that he called me, hey, Andrei, what did you do to SPICE? Because all of our analog circuits don't work anymore. Their bandwidth was cut by a factor of 10. Well, of course, it was cut by a factor of 10 because now this new model, it had capacitance between channel and drain, okay? So what was I to do? Okay, I needed to make both camps be happy. So I invented a parameter called XQC that actually you have even in BSIM4 today, which is called XPAR, which leaves it up to the user to say how much of the channel charge is given to the drain in saturation. And I got off this problem. So here we are in the 70s now with all the problems that I explained you. Industry was using it. Also, SPICE became a standard instruction tool in universities. We went further into development, as I mentioned, 2G6. Now, why are we proud of 2G6? Is because the first commercial SPICE software, known as HSPICE, today commercialized by Synopsys, was started as the basis 2G6. Of course, they did a lot more work in the 35 or so years since then. They added more user ease and analysis and so on. Okay, now today we have the leading commercial SPICEs are HSPICE, PSPICE, ELDO, Spectre is the cadence simulator, ELDO is the mentor, and HSPICE is the Synopsys simulator. There are also public domain efforts, but they're not at the level of the commercial versions. They still play catch up, but remember, these are developed by volunteers and students. So, and after the industry acceptance, it was the recognition by the IEEE that in 2011, at the 40th anniversary, they placed a plaque in the building of the electrical engineering building on the Berkeley campus, recognizing that here was born SPICE. And there was a special issue of the Solid State Circuits magazine with Don, with Ron Rohrer, and with Larry Nagel. I had also a contribution, an article telling some of these stories. Anyway, one take from here is that I had a keynote at the Bipolar Circuit Technology meeting in 1990, where, you know, without taking away from the contribution of SPICE or from the contributions to come, I stated that SPICE will evolve under new analysis modes, become more open to various levels of modeling, but will preserve the current fundamental algorithm. And this is really what I'll show you in the next couple of slides that happened. Okay, one important project was to build a parallel simulator called Classy on a Cray 1 machine. In the decades that followed, a lot of new functionality and new models were added. A very important part, as I said, the simulator will become more open. The community worked on building into SPICE a hardware description language, which is the Verilog A or Verilog analog and mixed signal, and the equivalent VHDL. Also tools for analyzing statistics and yield optimization. The final result is that today, SPICE simulators can handle over 100,000 transistors, going up to 1 million transistors in a simulation. How do we get more performance? Obviously, we don't want to wait weeks for the simulation results to come back. There are two aspects. First of all, using the multi-core hardware of Intel and NVIDIA to parallelize the solution following the effort on Classy. So we have the names, the commercial names change all the time, but with Spectre APS, XPS, HSpice XA, then we have analog fast spice and so on. And then the fast spice category itself, which is another group of spice simulators that uses some shortcuts that I'm not going to go into in order to gain time and performance. Okay. Now, in terms of functionality, a number of analyses were added, which is steady state, which is either in frequency domain or time domain, to get a settling of oscillator, for instance, envelope simulation. Now, in order for you to get a realistic simulation, once you have laid out that circuit, you need to do the extraction of resistors and capacitors, okay? And this is a very important part of your circuit verification before going to silicon. The semiconductor models need to keep up with technology. Obviously, you know that after 20 nanometers, bulk CMOS cannot handle the physical difficulties of the small structures. These were very well handled by BSIM4 and the PSP models. So going 22 and going down to 7 nanometers, you know, we have to choose between a fully depleted SOI or the FinFET technology, and there are models being developed for this one too. And so, as I mentioned, now SPICE can take advantage, or users can take advantage of all the new architectures like multi and many cores, the GPUs of NVIDIA, or, you know, for your convenience, you can even have it on your smartphone. There are versions of SPICE now on smartphones and tablets. Now, a new area of applications that SPICE has emerged in recently is for designing the electronics and the quantum processor. What happens? Well, you have heard of quantum computers, right? But so quantum computers depend on, let's say, for the spin of an electron. But how do you control what is the spin and the operations that that an electron must perform in order for us to get a computation? You have to send it signals, and you have to sense the state. Now, this controller, the electronic controller that does the qubit manipulation, is also going to be at a very low cryogenic temperature in order to be placed next to the quantum processor. As you know, the quantum processor, in order to be able to control the spin of an electron, we need to be at temperatures less than 1 Kelvin. Now, the unit of information in a quantum computer is the quantum bit. Now, the quantum bit is not 0 or 1 as in classic logic, but the state of the qubit, noted here with psi, can have any value between a 0 and a 1. So we call this a superposition. So the spin itself is in a superposition of state. And the implementation can be electron, nuclear spin, or the other things like IBM and other existing quantum computers today. They use the state of a Josephson junction resonator. Okay. Now, we need to design the electronics such that it generates the right signals to move the electron around what we call a Bloch sphere, right? So the state of the electron can be any point on this sphere where it is a combination between 0 and 1 state. These signals, the generated signals, the red signals, they must satisfy a certain what is called fidelity. So if you look at this table, you can see that you have very, very stringent values of how much the frequency of the signals can be, the amplitude, the noise, and so on. So in general, you tend to have like 10 parts per million accuracy in this building these circuits. So how can you do it unless you simulate it? And in the QTech lab at the Delft, we developed a new simulator called SPINE. It's based on SPICE, and SPINE stands for spin emulator. Now this emulator, it solves the synchronous behavior of the electronics and the quantum system. How do we represent the quantum system, or the qubit state each side? And then we have Schrödinger's equation, which is shown here, and gives the time dependency of the state depending on what is called the Hamiltonian, which Hamiltonian describes the entire system, the system quantum and electronic system, where here you have the frequencies of the signal and the amplitude of the signals. Now, somebody who knows SPICE thinks, wait a minute, but this is just an ordinary differential equation in time, exactly like a capacitor and an inductor. So if we start with a time-dependent equation, we make it time-independent by discretizing the points in which we solve this equation. We have a unitary operator matrix that we solve at each time point. So we have a quasi-static numeric integration just like SPICE, okay? So we sync the two time domain solution where SPICE is the controlling engine, and it may calls to a quantum simulator, quantum solver to solve this equation. And depending on how our circuit is, that defines the Hamiltonian, and therefore we can get the solution of electronics and quantum system at the same time. So the quantum solver is implemented as a Verilog A model to SPICE. And here we have an example where we have a controller as a behavioral model, the mixer, which gives us the length of the pulses we apply to the qubit in order to perform a desired rotation, and the qubit solver qubit model. And each develops its own behavior that the final result of a simulation is obtaining the variation, the probability of the variation of the spin of the qubit from a 1 to a 0, and the transition depending on the length of the pulses and the frequency of the precession pulses. Okay, we got to the end. I'd like to leave you with just a few main thoughts. First of all, SPICE is not a black box, okay? Why? Because you see, SPICE is used to solve all sorts of different equations, going from volts to kilovolts, from nano or picoamperes to milliamperes, or to 100 amperes for power application design. So a large variation of these quantities. Therefore, SPICE lets the user define what are the tolerances, because you saw it is an iterative process, so we need to define error tolerances and accuracy. So a knowledgeable user will get more benefit out of SPICE than an unknowledgeable. Maybe this is a little bit too strong here. So the smart user kind of knows and questions SPICE if he gets an answer that he doesn't expect. Is this right? Well, uninformed or dumb user, he goes ahead and doesn't understand why he gets a result, but his defense is, well, SPICE told me so. So it's not my fault that the circuit doesn't work, okay? Now, people ask also, what is more important, algorithmic accuracy or model accuracy? Well, you can imagine it's a chicken and egg problem. The only thing I can tell you, the simulation is only as accurate as your model. So if your models are inaccurate, the simulation is not going to be worth much. Okay, universities and R&D centers are an important group in developing models, especially. And it is important that there are some public domain efforts like NGSpice and SPICE. What is the explanation that SPICE was the one program among several developments in the late 60s that reached universality? I think that placing in the public domain was the key here, okay? Now, key algorithms were developed by 80, but after 90, there was a lot of new functionality and new classes of circuit added. The device models are driven by technology, so if anybody likes device physics and gets into this field, it's an insured employment for the rest of your life, because technology is changing all the time, and every time you need to develop new models. Okay, I would like public domain. We don't like to close our achievements of research in ourselves, because SPICE is an example how a public domain, a university effort put in the public domain led to an excellent tool, without which today's development would not have been possible. And don't worry, SPICE is everywhere and it is here to stay. So you better learn it. Thank you very much.
Thank you very much to you for this nice and interesting presentation, Professor Andrei Vladimirescu. It's always interesting to know that how the electronic simulation by computers has improved so much since so much time, and it's novelous nowadays, actually helping us to develop our circuits, and it's running in the background in the heart of the simulation. So this is in fact interesting. And it's also good to know that there are also some new development focused in the quantum computing fields. Well, so now to begin with the questions, first we have a question from Kevin Arise. His question is, thank you for this nice presentation. What can we expect in the future, let's say 5 to 10 years, regarding simulation tools? Just the speed, or also new ways to make the simulations?
Well, let me start the other way. I will start with saying what you cannot expect, even in 10 years. The simulation tool is not going to make the decisions for you. This is pretty much clear. Now, what we can expect is more and more analysis. So, big data is a big word, but actually the larger the chip, the more and more data and information you obtain from the simulator on behaviors, on details in specific places of the circuit. So I think that getting more analysis tools, analyzing the results and give them a better introspection into these results, helping the designer find if there are problems. I think that this is a field that needs. Of course, also compute technology is going to evolve. Maybe someone will figure out how to solve differential equations faster on a quantum computer, and that will be also a big step forward, because even with the fast devices today, it takes a certain amount of time, that means days, for simulating hundreds of thousands of transistors. So this is a little bit the directions that I see.
Okay, thank you very much for your answer. We have another question from Professor Yandeval, which says, when it comes to event-driven or asynchronous clockless or digital chips, do we have to go back to analog simulations, SPI-like, to check the huge integrated circuits? And if yes, is there any chance to reduce simulation time to acceptable levels?
Okay. I'd like to start with the story. I was in a company with signal circuit, and of course you have the analog designers and you have the digital designers, and each did his part, and then they put the the Verilog that used you know fast the ability to have event-driven. You have blocks in defined blocks in the system that can be analyzed as event-driven, but of 0 and 1. Between analog and what doing it.
Excuse me, Professor Vladimirescu, I think there is a problem with your microphone.
Okay, well.
Okay, now it's good.
Can you hear me now?
Yeah.
Okay, so to make a long story short, the problem was in the digital part, because the digital abstraction, not taking into account levels of voltage and current, they had made a mistake there, and the digital part was not giving the right answers, and that's why the chip didn't work. But what is fantastic is that using this fast price, which can actually use different time scales for different blocks in the circuit, but still keeping voltage and current representation for the digital part, we found the problem. Did I answer your question? Hello?
Yeah, thank you very much for your answer. Well, there are no more questions from the chat. I also have just more questions. Is this spine emulator with its qubits model, it's available nowadays from the providers of the spine commercial, like Synopsys or Cadence, for development, or is just a matter of improvement? No.
Sorry.
Excuse me, there is a problem with the microphone again. No, it's not working.
How do I get to the chat?
Now it's working.
Okay.
Yeah, the question is this new development of the spine model, it's available commercially?
Can you hear me now?
Yes.
Okay. So about which simulator were you asking?
The spine, the new one from the quantum computing.
Oh, Spine. Spine is a university effort. It's not a commercial product. So Spine was developed at QTech by one of our PhD students, Jeroen. Jeroen had the idea, and he saw the possibility of coupling the two, but it is not a final, product ready to give out. We were talking about who wants to experiment with it because it's limited to spin qubits, not to Josephson junctions, and it's limited in the purpose of the interaction of two qubits, because the power of a quantum computer comes from the fact that while you have more qubits, the power of computation increases exponentially as power of 2. Okay? But right now, the demonstrator, the spine program, can handle only 2 qubits. Okay? So there is still more work, and probably one day it will be available.
Okay, thank you very much for your answer. And just another question for curiosity. During this whole period that you were developing this SPICE model and SPICE simulator in the 80s and 70s, there was another competition from other teams and other universities, just for curious?
You mean back in the 70s?
Exactly.
Well, yeah, there was competition. There were a number of attempts. So I mentioned the IBM effort, and it was, from a mathematical point of view, it was a beautiful solution. It was different than modified nodal. They called it a sparse tableau approach, where you are mixing current and voltage level equations on branches. But the developers made one error. They thought that models were not important to be part of the program, that they will be as a library or the designer himself. So the difference was that SPICE was developed by engineering students, whereas the other one was developed by mathematicians. And then it was commercialized by salesmen who wanted to make money. So that's why, ASEP, for instance, never made it. Then there were other attempts to try to, to take over SPICE. The names don't come up right away. But in the 80s, there was a lot of competition of different simulators. Everyone tried to say that they're faster than SPICE. But eventually, none of them could prove it except for limited classes of circuits.
Okay. Thank you very much for your answer. It's very interesting. Well, I don't think we have any more questions. So thanks again, Professor, for this nice presentation and your time to give us your talk.
Thank you very much. It was a pleasure. I hope you enjoyed some of my stories, because I don't like to make a dry talk, but bring in some of the facts and some of the difficulties, because any new discovery is also partly painful, and you have to go to the pain in order to get to the result. This is one lesson that I learned.
That's good. It's always good to know the roots of our electronics branch. So certainly, it's very interesting to know.
Thank you very much. I enjoyed, and I hope you did too.
Thank you. Well, finally, before finishing, I would like to remind everyone in the chat that we will have more presentations. Our next presentation is going to be in 2 weeks, given by Professor Jean-Michel Redoute from Belgium. And it's going to be more focused in electromagnetic compatibility. So stay tuned and take advantage of these conferences and another talks that are going to be given even during these times. So I hope you all enjoy the talk. We will meet you again in the next talk. Bye, everyone, and take care.
Bye-bye. Thank you.